Good afternoon. Welcome to this webinar on directed energy deposition and hybrid manufacturing, arranged by Future Materials Norwegian Capital Center in collaboration with Mechatronics Innovation Lab and DMG MORI. First, I would like to encourage all of you to use the Q&A in Teams for your comments and questions during the webinar. We will try to answer as many of these as possible during the discussion at the end. Some of you may know the Norwegian Capital Centers already, but for those of you who are not familiar with this scheme, I will briefly describe what we are. Our mission is to accelerate the process from concept to market launch in product development. We have a focus on small and medium-sized businesses, but are also working with larger companies, entrepreneurs, academia, and research organizations. We provide premises, equipment, and competence for testing, simulation, and visualization of technology, products, and solutions. So, how do we do that? Future Materials has, as you can see on the right side of this slide, very skilled partners and owners providing the relevant competence and equipment for material testing. Through our capital centers, you as a company, a university or research institute, will have access to all the test facilities at these premises. Equipment with a total value of around 725 million Norwegian kroner. This is really sharing economy in practice. Today, we will present one specific technology which is available at our partner Mechatronics Innovation Lab, the DMG MORI Lasertec 65 DED hybrid. I am delighted to hand over the scene to the CTO of Mechatronics Innovation Lab, Morten Bach.
Thank you very much, Aslak. I hope you can all hear me. If you will just give me a second, I will share my slides. And Aslak, if you can hear me and you can see my slides, just give me a thumbs up or something. Okay, good. Thank you so much for the introduction, Aslak, and I'm very excited to be able to talk to you about this topic, and even more excited to hear about what Dirk from DMG MORI has to show us afterwards. As already said, my name is Morten Bach. I'm the CTO of Mechatronics Innovation Lab, and I will be introducing this topic that we'll be talking about today, easing into it, you could say. And then afterwards, Dirk from DMG MORI will go into much more detail. But before I get started, I'll just like to spend a few words about talking about Mechatronics Innovation Lab. And Mechatronics Innovation Lab is a test and innovation center, a national test and innovation center within Mechatronics. We are located in Grimstad, just next to University of Agder, who is our majority owner. And there is also another owner, which is Norse Research. As you can tell from our name, we work with everything that has to do with mechatronics, all the way from actually to some extent materials technology and additive manufacturing, as we'll be talking about today, all the way up to automation systems, robots, sensor technology, AR, VR technology, machine learning, etc. And our main purpose, in short, is to help the industry, become more innovative and adopt new technology. So that is our main purpose, and we do that in several different ways that we can talk much more about in another presentation. But today I have just chosen to bring a video, and I'm always excited to see how those videos works in these presentations, but we'll give it a try. Okay, that was just a short teaser as an introduction to what we do. I'm not sure how that video worked on your screen. On my screen, it looked fine. In case it didn't work so well, you can also find information about us on social media, Facebook, LinkedIn, etc. And the video should also be there. As Aslak had already mentioned, we are also, of course, a proud partner of Future Materials, together with all these other partners and owners that you see here. So, onto the topic of today, and just a brief word about additive manufacturing. As you probably already know, additive manufacturing is very different from other manufacturing technologies, such as subtractive manufacturing as machining, or formative technology, in that we are adding material, and not only adding material, but adding material exactly where we want it. And that saves, first of all, material. It gives them some design freedom, and also it eliminates the need for a tool. So it's a tool-free manufacturing technology, you could say. So hybrid manufacturing is usually a combination of several manufacturing technologies, and as you might also be aware of, that with additive manufacturing, we almost always have to go through some sort of post-processing, whether it's heat treatment, surface treatment, or post-machining. So you could argue that whenever we are dealing with additive manufacturing, or formative manufacturing, for that matter, we are always doing some sort of hybrid manufacturing. But what we're going to talk about today is a much more integrated approach, where you're using additive manufacturing together with machining, using equipment that possesses both capabilities. That, as I already mentioned, gives you a much more integrated approach, and actually allows you to switch between those manufacturing methods several times during the process. So just a brief overview here to show you that additive manufacturing is a very wide field, and there's a lot of development going on actually, and additive manufacturing as such is not a new field. Several of these technologies that you see here is several decades old, some of them more than 30 years old. Obviously, as I said, a lot of development going on, both within these existing technologies and also new technologies emerging. But more or less, they are all located or categorized under these top categories that you see as these 7 categories. We will not go into all of those today, just to make clear that this is this category, the directed energy deposition category, that we are talking about today. Looking a bit further into what we call directed energy deposition, as you can see here, we also have several subcategories here, and there are certainly different ways that you could look at these subcategories. This is one way to look at it. On one side, we have the powder-based methods, and on the other side, we have the wire-based methods. And under these subcategories, we again have several subcategories. For the wire-based methods, we have arc plasma methods when we talk about the energy or heat source. The arc plasma methods is basically your standard welding methods, TIG and MIG methods used for additive manufacturing. We also have laser-based methods here, and electron beam based methods. For the powder-based technologies, we are usually talking about laser-based methods. There might also be other methods here, but at least the laser-based method is the most popular one. So let's have a closer look at that. As with all other fields, there are a lot of abbreviations, and additive manufacturing is no exception. So the category that we're talking about here, the directed energy deposition based on powder and laser, is also sometimes referred to as laser engineered net shaping. That's kind of the formal abbreviation. I would say it's probably not the name that is used most often, but in case you ever see that name, you know now what we're talking about. Some of the more common names is laser metal deposition, LMD, laser deposition welding, and laser cladding. And they are all names for the same approach or method that we are talking about here. So obviously we are talking about a method that is based on a high power laser used to melt the powder and fuse it onto the substrate or the previous layers. And by a high power laser, we are talking about a laser that is down to a few hundred watts up to a few kilowatts, typically somewhere in the range of 1 to 3 kilowatts. But that's of course very system dependent. We're also using a shield gas as in any other welding method. Only here we are using pure argon as a shield gas, not only as a shield gas, but also as a carrier gas to carry the powder down to the melt pool. And then, as you can see here in the picture to the right, you can see some of the characteristics of this method. One of the advantages of this method is that it has a relatively high build rate compared to other methods, but the downside of that high build rate is obviously also that the resolution that we're able to build with is relatively low, that the surface quality is kind of rough, you could say. So I would say more or less always there is need for some sort of post-processing. Typically machining, as you can also see from the top of this picture, could also be grinding or different surface treatment methods. And that's where we come into the hybrid manufacturing method. This is the equipment, the machine we have at Mechatronics Innovation Lab, the DMG MORI Lasertec 65 DED hybrid. It's a long name. And it's basically, it's a 5-axis milling machine with a laser module on it that we use for the laser cladding. Here you can see the spindle. It's a 3-axis spindle that can move in the X, Y, Z direction, providing free of the axis. And it has a rotating table down here, providing the 4th axis, and it sits on a cradle that provides the 5th axis. So here we can machine in 5-axis, and we can also deposit material in the 5-axis, in 5-axis. Because the same spindle we are using for machining, we are also using for the deposition. Here you see the laser head in the laser module that is used by the same spindle. And what that means is that we can not only machine in 5-axis, we can also deposit material in 5-axis, and that has several advantages, as you will see in this video in a couple of seconds. It means that we are able to tilt and rotate the base, and one of the advantages of that is that we can eliminate the need for support structure that you would have in other methods. So just a short video here to show you how the process works. It's of course just a demonstration piece here, actually shown on the machine we have in the lab, but it shows you kind of the capabilities of the machine here working with all 5 axes simultaneously. Yeah, so that was a short introduction from my side, and then I would let Dirk from DMG MORI take over, and then at the end of this webinar, I will come back with some examples of some projects that we have carried out at Mechatronics Innovation Lab.
Thank you, Morten. And then I would like to hand the word over to Dirk Rohde, who is Product Sales Manager, Advanced Technologies at DMG MORI. The floor is yours.
Yeah, thank you very much. Thank you very much, Morten. So with your great presentation, I'm almost done. You explained the machine really good. Nice videos. I would say let's share that. Now, let me switch to my screen. Should see it now. Yes, I would like to dive a little bit deeper into this theme of DED. The name DED is coming more and more, laser cladding and all the other words step aside a little bit. The international knowledge of this process, it's covered, or it will be covered by DED for the future. So the industry has focused on this name because it says a lot, and that's the name or the reason why we renamed our machines to the Lasertec DED machines. Short word about DMG MORI, who is not knowing the company. We are traditionally coming from turning and milling machines, traditional universal machines with a wide size range from very small entry-level machines up to 6-12 meter machines. A couple of years ago, DMG and MORI decided to go together. At the end, MORI got more money for a lower fee to take over the full market share of DMG MORI. We have 14 production plants and worldwide over 12,000 employees. The interesting thing is, due to the global presence, we have service and additive manufacturing experience centers all over the world, where we are capable of doing tests for customers. The field of so-called advanced technologies, beside the traditional milling and turning technology, is growing. So at DMG MORI, here we cover the ultrasonic grinding of hard and brittle materials, like any kind of ceramics and many glass parts, coming more and more in the semiconductor industry, and as well the Lasertec and the additive manufacturing. So in combination with the laser, we have a very, very wide range of laser works. We are active in laser shaping, in which we texture or work, shape or ablate in parts on an industrial basis. We finish diamond tools. We have the power drill section where we drill or shoot holes into parts. And we have, of course, the additive manufacturing section in two fields. We do the SLM and the DED area of this, with a very wide range of machines, and the machine variation still growing. I come to that a little bit later. SLM, yes, why? It's a very fine, detailed and industrial approved additive manufacturing way. And the DED, that is resulting on the idea for a real hybrid part in which you additive and subtractive in steps forth and back, however you want it. As Morten said, we have the, in the spindle, instead of the cutting tool, we have the laser head. In all our hybrid machines, we can load and unload the laser head and change to the tool itself. It's not necessary to completely finish the DED process. You can change in between the process. So on surfaces that you cannot achieve later on, you can unload the laser, load the required tools you need, and machine the surfaces. The DED, just as the last word, DED is, see that in the table, DED is not a research theme anymore. It's really industrial approved. The machines itself have a really interesting process control, a self-regulating process control, which allows you to work operatorless over hours and hours, because the machines are controlled for the process. The benefits, it is good that Morten gave me such a great base. The benefit is overall and in general the hybrid idea behind it. So only printing or only printing of parts in that machines, it's typically not beneficial. These machines are the advantage of these machines is in the high speed of repairs, and the high speed of bringing parts into shape, take off material, add material, and finish it with the milling process at the end. With that, you save enormous time and, of course, money. The Lasertec 65, Morten explained how it works. All machines are based on 5-axis milling machines with the same precision. There's no limitation to the milling process itself. We have the tool changer, we have coolant, water running in the machine. Everything is there. The full Siemens control is there. So really no limitation. In addition, the Lasertec comes on top of this 5-axis milling machine and off top of the capabilities of the 5-axis milling itself. Machine sizes, milling machines. A little bit over a year ago, we presented the last stage, was a Lasertec 125, which has a round table in the middle with a diameter of 1250, and it can handle up to 2 tons on the machine table. This allows you to really bring on big parts. The focus was on 1200 millimeter plastic molds, as well as pressed dies for the chassis industry. We also have actually one Turnmill machine. The first one is located now in the United States. The first installation is has just ended a week ago. This machine, you can see the operator standing in the front of the operating panel. This is can be grown up to 6 meters in between the spindles with a brand new laser head. So the typical build rate or the typical application rate of the Lasertec machines was a little bit below 1 kilogram material per hour based on steel or stainless steel. With this new head, we will be capable of adding up to 3, perhaps a little bit below 4 kilogram an hour. It's a brand new design. It allows us to swing this head, and in our new Turnmill machines, it is, or it will be possible to finish parts 6-sided by loading from the main spindle into the counter spindle and work and finish the 6th side. Yes, you're right. Some or many people are thinking, whoa, that's a really big machine. I don't need that. A smaller one is coming, 1500 or 3000 millimeters between the spindles. The launch is planned for end of May, so very soon, a couple of weeks in the future. So I ask for your understanding that I'm not allowed to tell much more about it. The most important reason for Aslak and Morten to invite me is to tell a little bit what is possible and where it is needed for to give ideas, and that you can find yourself in the field of hybrid manufacturing, or even not, can also be, who never knows. As I said, the main focus is not printing or building of big parts. It would take hours and hours and hours. It may be interesting if only one part is necessary or expected, or two parts are expected a year or so. We have customers, they do that, yes, but the most industrial application is a combination of repair and a base to manufacture parts that cannot be produced or manufactured on a traditional way. Here, first one at the bottom, we have a cutting knife. The base is Ferro 55. It's a proven tool steel. The build rate on that one is not too bad, 850 grams an hour, but it has only 55 Rockwell. And this is a cutting knife for forged parts. The top cutting corner, the cutting knife, the ring, is made by M2. M2 is a high-speed cutting steel. Yes, typically high-speed cutting steels are not weldable, but it is available as a powder, so we can work with it. And this M2 high-speed cutting steel comes out of our DED machines with a hardness of over 60 Rockwell. So 62, 63 Rockwell is typical. So this part is completely print machined and finished on the machine in one step. The next part, few slides later, I'm going to explain that a little bit more, why the lifetime is so high and where the benefits for this. That's a die cast. And the third part is a typical repair part from the chemical industry, in which the customer has many plants all over the world. Very old valves like this, and yeah, no drawings available, no models available, but they have to replace it from time to time due to the environment or due to abrasive materials going through. This full print takes a little bit over 50 hours. It's stainless steel, and what the customer does is he takes a hand scanner and he scans the area where these old valves sit, and then he has the dimension, overall dimension of the valve that it fits, and the only thing that is interesting are the flanges. The internal geometries will be based on modern state-of-the-art standards to be able to order seals and the knob to close and to make the this valve work. So every valve is a unique part, and they or to get a casted material, the price would be tremendous high for a single part, you know. This is a cutting knife Morten presented. That was for a tooling company. Here's the same. We have a very cheap and fast printed base, which is Ferro 44 Rockwell. This is obviously not hard enough to realize alive as a cutting knife. So we add an approximate 2 millimeter layer of this M2 material. It is printed and machined, as I said, in one step. It takes only 6 hours until this full cutting knife comes ready for the insert into a tool out of the machine. This is a sample we made ourselves. You know the powder bed machines, everybody knows it's a single material process due to the fact that we blow the material in our machines from the hopper to the melt point. It makes it possible to switch even in one layer or from layer to layer to switch the materials. We have a twin feeder system in our machine, and we are able to mix the materials. And here you can see a stainless steel body, which is a tube-in-tube solution here, and we have a bronze for in the inside, and we switch the material from the outside to the inside in one step, which is a simple blowing impulse to clean the feeder or the feeding tubes and to load the new material. Perhaps as a side note, the powder of DED machines is much bigger than the powder of SLM machines. The SLM powder is typically from something from, let's say, 5 micron up to 35, 40 micron in a single ball size, and the DED powder typically starts at 55, 60 micron up to 120, 125 microns. So this, or the result is that this powder is not so dangerous. Theoretically, there should be no airborne particles, I'm sorry, not articles, but we always recommend to wear at least a simple face mask like you have for Corona, and gloves. On the other hand, if you work in a hybrid mix, additive, subtractive, typically you have the coolant water, and that flushes all particles away. This is a part for our Lasertec 400. It's a hybrid part on a hybrid machine. You need always a base plate where you start your welding on. I mean, me as a sales engineer, I'd love to sell you every day or every week a new machine table. But if you start here with this pre-machined base plate and you build the structures in between the two plates, it is also possible then, that is what I mentioned with hybrid machined process. We have the base plate, we add with the DED process the structures in between the plates, and then we lay this other pre-machined plate on top and we weld it in the machine. And in the last process, we add this front end to simply where the laser head will be installed. I'll jump over this because I will show you some more details about it on here. In the top left, you see the die cast used coming out of the machine. It's then simply cleaning process, and then we have to identify the used or the weared sections of these die cast. They are colored upper middle section. And then with the machine, with the, in this case, the 65 DED, we machine or we mill all the used and or weared sections off, add the material again, and machine it to the final dimensions. And it comes, as you can see here in the lower middle picture, it comes ready for the next insertion into the die cast. I'm sorry, into the die cast mold. It comes ready out of the machine. And that's what I said, where the DED technology is a real weapon. In this case here we have the same. Another die cast. Identified the word surface, the word areas. You mill that off. You build your support, and the support means the base of it. You coat it, you cover it with a Ferro 55, and then you simply take the material, the material that is too much on it, take it off. You extract the area where you mill a little bit, and a finished, ready-to-use part comes out of the machine. In this case, within only 2 hours. Yeah, and this is not possible by manual work or manual welding. This sample shows it probably a little bit better. Top left, you see the identified rib in this case. And at top right, you have the photo where this rib has been machined off. And then in the third picture, this rib has added in the tool. And then on the right, you see the finished, repaired die cast again. It's in 1 hour. Only this customer has, in the meantime, 3 Lasertec 65 machines to repair die casts. This is something to give an idea about it. This is hybrid machining of parts. Again, you have the blank part, and then you machine it in the step 2. Start with the impellers, take it as a core, and then in the next step you add the material all around it while you form out the impellers itself. And it's possible, or in this case especially, the customer changes between additive and subtractive. So every surface in between the upper and the lower disc, what you can see here in the yellow, has been machined. Due to this fact, it is possible to have the radius much more smaller than what was possible before, because everyone who knows these impellers, you typically have this long lollipop milling tool, so-called, and you really lose time because they're so soft and flexible. You cannot really make chips with it, and it takes time and time to machine the surfaces. And that's the restriction for the design engineers for the radius of the impellers. This is gone. In this case, the designers have an unbelievable freedom to make those impellers really efficient. Yeah, at the end, simple overview, current process steps, what is typical, and what can be done with the Lasertec 3D hybrid machine in one step on one machine, in one piece flow, so you have no part touristic from your welding department to your milling department and then to your measuring department. Perhaps you have an external stress relief department, so you lose more time by moving the parts than you really spend on time to make it work again. Here are the today's possible materials. We have the process parameters. Generally said, in every material that is available as a powder can be typically welded with this machine. It's still a laser welding process. Due to the machine size and our way of those, or using those machines coming from a milling 5-axis precision milling machine to a DED hybrid machine, is that we cannot seal the full working room of it with argon. So unfortunately, we are not able to handle reactive materials like aluminum and titanium. We made tests with it, but we still have too much oxygen somewhere in the machine. Yeah, so no reactive materials, but every other material which is weldable in this machine can be used. Yes, it's a simple screen. It's a very stable process, and it's reprocessable as soon as the parameters has been set or have been set up. You typically have no holes, I'm sorry. Yeah, no holes, no. I'm missing the English word. I'm very sorry for that. It can happen.
No pores, low porosity.
Low porosity. Thank you very much. Always good to have a souffleuse in the back. Yes. Twin feeder system that allows things, many things. Here are two very important things: a material mix and combination of materials. So here you can see the stainless steel and bronze mix again. The bronze can feed the heat much faster away than the stainless steel is able of. And on the other hand, we have so-called grated materials. So you can fade over the materials with the with this machine. We made that with magnetic material. We had a non-magnetic material, and we faded to a strong magnetical field for electromagnetical soft stops in linear modules. That was a really physician story at the end, but it worked well and gave us the ideas about it. Material mixes and substrates are coming more and more. There's a brand new alternative to a pure copper out in the field, and many companies are working on material that can be easily handled with those machines, because the expectation and the requirements from the industries are there. Yeah. This is a great sample of a part that is not, you cannot manufacture it on another way. We have a copper core with coolant holes in it, with a tool steel surface. Yeah, this reduces the scrap by only a few percent, but it's a high volume part. At the end, it saves so much money by simply change the way of manufacturing it. And the way of manufacturing this part is not even much more expensive than a traditional part. It's just a new thinking of using of technologies and material combinations in combination with the coolant holes in there. And that's not possible on a traditional way, because it simply starts at how you drill the holes for this. Yeah, coming close to the end. I'm happy that I'm in time. This is a simple overview that what we have made, a different idea here. In the past, they took a full solid block and they machined all the material around away and throw it in the garbage. What they're doing now is take a simple plate and build these two stands in here. Process control. In the very beginning, I said that this machine is controlled. We learned a lot over the last years. The machine was presented 8 years ago in 2013 for the very first time. What we have to make it sure that the machine runs after you started it, after the process parameters has been set up. Before you start, we have the powder calibration, that the machine calibrates the powder weight and mass by itself over a weighing process. In combination with that, we have a powder mass flow sensor that we know that powder is coming to the nozzle of the machine. We have a melt pool monitoring that is adjusting the laser force in the process by using the heat camera. A distance control camera that gives you the necessary, or the possibility, or on a different way. If your CAM program calculates 1 millimeter grow per layer, and you have 1.1 millimeter per layer, and you have a really high part, after only 100 layers, 100 millimeters, you have 1 millimeters more, and your melt pool is not in the focusing point anymore. Yeah, therefore it's a distance control to keep the distance, so which means the focus point always in the same spot, in the same relation to the head, allows you to stay in the same quality for the full build time. The working room camera allows you to check for new jobs, how your heat moves into your clamping tool, hopefully not too strong in your table. The nozzle adhesion detection, you see that here in the side. It's a through camera through the laser, and it detects if the nozzle is it's going to be closed very soon, so that you can break your process, choose a spare nozzle and restart it again. So far, that was a lot, I know, and I promise you that was not everything. I had 30 minutes only, so I didn't tell you much more about the machine in general. There are many, many more other things. I'm happy that you joined this webinar. I hope I could give you some ideas to decide, yes, this might be something interesting for us, or this not, or whatever. At the end, we'll share the contacts, I would say, and in the question and answer session, I'm here for you. There are no stupid questions. It's just feel free to ask whatever you are interested in. Thank you very much so far, and yeah, I would like to hand over to Aslak.
Thank you so much, and thank you for your presentation. It was great to have this overview, Dirk, so thank you so much. And thank you to Vegard for your clarifying comment published in the Q&A. And I will also encourage you to post the questions during our last presentation, which is Morten, again, presenting some of the projects from the machine that we have at the Mechatronics Innovation Lab, hopefully giving you lots of ideas for projects that's interesting for your company. So please, Morten.
Yes, thank you, Aslak. And yeah, thank you, Dirk. I think it was a really interesting, great presentation. I think this is a really interesting technology. It's different from other AM technologies like the powered bed fusion that was also mentioned here. As you can see, first of all, you are able to build much bigger parts. You can combine materials, etc. So it's a really interesting technology, and which also should be, I think, very interesting for many companies in Norway. So here at the end, just a few examples of something we have been working with at the Mechatronics Innovation Lab. What you see here was one of our first projects, or yeah, just a small trial actually to get familiar with the machine and the technology. It's a little cute example of a cross for a stabilized, what do you call it, platform for an ambulance actually, with this kind of cube in the middle. And obviously you could also just machine this from a bigger piece of material, but in this way you save some material, and perhaps you also save a little bit of time, but at least it's a good example of to show how this hybrid manufacturing technology works. Here's just a short video showing a part of the build. Right now the laser is it's waiting a little bit for the previous layer to cool down, and that's very important, because if you just keep on welding on the previous layer before it has cooled down, you will not end up with the material characteristics. So that's important, but that's way into the details that we don't have time for today. Another example is a project we did, I think, back in 2019, so 1.5–2 years ago, for one of our customers, Mechatronics, which is one of the leading suppliers of offshore drilling equipment, so-called topside equipment. And one of the things, one of the machines they make is a pipe handling crane used to handle the drill pipes. It has a gripping head that you see here that grabs around the pipes, and in order to join the pipes and unscrew them, there are these rollers that has to roll along with the pipes when you do the makeup and breakout. And these rollers, obviously, this is what a roller looks, is exposed to a lot of wear. And for that reason, there are two areas in either end of the rollers that is has a wear-resistant layer with this profile you see here. Yeah, it's exposed to a lot of wear. As you can see here, this is how the roller looks like when they have been in the field for a certain amount of time. Not sure how long, but anyway, as you can imagine, repair on a platform offshore is expensive, and of course downtime is also very expensive offshore. So Mechatronics here wanted to see if they could introduce a new method and also a new material to increase the lifetime of these rollers, simply make them last even longer than they were doing today. So we found a suitable material together with Mechatronics and also with good help from DMG MORI, and we actually produced a small pilot series of these rollers in the machine. Previously, the rollers were turned out of one piece, and then these areas where you see the grooves were hardened afterwards. So what we did instead here is we produced the roller itself, the base material, from a cheap, simple piece of steel, because here you have so much material that a simple construction steel is more than good enough, and it's easy to weld on and it's easy to machine. And then in the areas where we really needed the wear resistant, we added a very hard wear resistant but also impact resistant tool steel. Unfortunately, I can't tell you which material was used here, but I can confirm that the hardnesses and the quality of the tool steel that is difficult to weld, I can confirm that what Dirk said previously is completely true. We achieved a very, very good hardness directly after the laser cladding process here, which was as expected also. So as also previously mentioned, this method usually requires some post treatment here, and was also the case here. Instead of the machining the parts in the machine here, we chose to grind them, and it didn't have to do the machine. It actually had to do with the material, that the material was so hard that it was just much easier to grind it down to the final shape. So here you can just see some examples of these rollers that we made. And after that, we actually did a test at Mechatronics to really see, to really stress the rollers and the rollers were set up in a gripping head, a test gripping head, and we clamped around a pipe that was rotated with the actual speed to see if how this wear-resistant layer held up. And after actually a prolonged test, which was a real stress test compared to what is how the rollers are actually used offshore, we could see that they held up very, very good. This was an extreme stress test, and the debris you can see here is not from the rollers, it's actually from the pipe. So they held up very, very nicely, and MHWH was so happy with this that they actually chose to send off this pilot series of these rollers that we made offshore onto a rig where they were field tested for I think 2 or 3 months and showed very, very good results. Okay, final example is something that we're working on right now, and it's actually not directly related to hybrid manufacturing, but more to the DED process, the laser cladding process. It's a research project that we're doing, that we are involved with Elkem, who is a project owner, and we're working also together with all these partners you can see down here. And the purpose of the project is to develop new materials that can be used for additive manufacturing. In this case, silicon-based materials. And some of the advantages of such materials could be, for instance, what we saw just before, very hard and wear-resistant materials. So actually, here's some pictures from a test that we did last week, just to of course, I can't disclose the results here, but just to give you an impression on what we're doing in this project is that whenever we're dealing with a new material, as Dirk also mentioned, we have to develop the parameters, the right laser power, the right scanning speed, powder feed rate, etc. There are roughly a handful of process parameters that need to be developed, and that's what we have been doing so far in this project. Here you simply see some test coupons, as they're called, with different parameter variations to be able to find the optimal parameters to give the best possible quality of the final products. So this is just to give you an impression of what kind of activities we are also doing at Mechatronics Innovation Lab, and some insights to some ongoing research work that is actually being done in Norway, which I think is very, very exciting. I think that's actually my last slide. So thank you so much for attending so far, and I think maybe we have time for a few questions.
We have 2 minutes left, but there's no questions in the Q&A. I guess that the people will probably contact you after the webinar instead. So I would just like to say thank you, Dirk, and thank you, Morten, for your wonderful presentations. Very interesting. And thank you so much to all the attendees that attended the webinar. I will send you a link also of the recorded webinar, so you can have that and look into the parts that you missed, if there was any of them, and also the contact information for myself and of course Morten and Dirk, so you can contact us directly if you have any questions. So thank you very much and have a great afternoon.
Thank you so much. Bye bye.